Welcome you all to this video lecture. In this video lecture, the main aim that I have here is to overview the modeling. So, if we start with mechanical systems, so we can broadly divide motion actually into two parts. One is linear, other is rotational. So the basic idea behind linear motion is that you are moving in a particular direction. In rotation you are moving around momentum or some fixed angle. Okay. Now here in both cases we use actually Newton's second law of motion that says that sum of forces here is equal to ma, but here in rotation it says sum of torque is equal to inertia alpha. Alpha is the angular acceleration, here is the linear acceleration mass, here I is the inertia. Now before moving further, if we look at component quickly, so we have mass, basic component that we want to move in a particular direction, and if it is moving along some displacement, say x, so if we apply a force in that direction, so this force becomes F is equal to mx double dot, because acceleration is the second derivative. So similarly, if I have to look in case of rotational and it is connected with some motors or something that rotated into a particular direction, say torque within theta in time. So if we apply the relation here is torque is equal to J and theta double dot of t. So this is the basic component in both cases. Now if we move to next one, so next one we do have is known as a damper. So there are different ways of representing this coefficient. Some represent by B, some represent by what you say D, but it doesn't matter. So unless you understand what's going on, let's suppose it is represented by B, and again forces applying in this direction. So in that case this damper is actually related with the velocity, so it becomes B times x dot. So if a damper is connected with some rotating component, so with the torque and theta, so in that case this torque is equal to B times theta dot of t in rotational motion. So the last one we have is a spring. So we know that the constant is k, and if we apply spring with a force and move in that direction, so this is with the displacement, so it becomes fx. So similarly, if we have a torsional spring here that can move in a rotational with the theta with the applied torque, so it becomes is equal to if this spring constant is k here is theta of t. So this is the basic idea that we use to model the system. Now let's look some examples quickly and try to understand. Let's suppose we have a system and it is connected with a spring, right? Now then there is a mass, and then there is a damper is connected. Okay. The damper is connected with that. Let me try it again. The damper part is not drawn well. So, and damper is connected. Okay. Now after that you have this side. So this constant is k, this constant is b, and the direction that its move is y of t here, and we are applying on force on this mass. So we can model it very easily. We know that if we have to write, we have to use the second Newton's second law of motion, that is m alpha. Now here, y is the displacement, so we can write the sum of forces. So what are the forces? The force that is created by spring and damper is actually opposing force. So if applied force is u of t, so u of t minus opposing force due to spring is ky of t. Similarly, the opposing force due to damper is b y dot of t is equal to m y, and you have to take the second derivative. So this is the equation you can get, or some people write like u of t is equal to my double dot of t, and they plus here the force is by dot of t, and plus k y of t. So this is the way you usually write the equation here for this system. This is your example 1 for this video. Now you can do manipulation on this example. So the basic idea is to look at the free body diagram here. So here is the free body diagram mass. You have to write the forces, and then you have to write the opposing force that due to mass, opposing force due to damper, and opposing force due to spring. So this is the another way of easily finding the equations. Okay. Now let's look at another example and make it a bit difficult and try to solve it. So this is an example. We have a cart. You normally see a cart, and its cart is actually moving. Okay, it has 2 tires here, and this cart is moving, and its cart has something on it. So for cart we say that this is for assumption we say that this is massless cart. This is not true in reality, but we assume for this example that this is massless cart. Okay, it has 2 tires, and then we have a spring connected to a mass and a damper. Okay, so this is spring, this is mass, damper, and mass is m. And mass is also a tire that can move. Okay. Now this mass is moving with the displacement that is y of t, and this cart is actually moving with a displacement represented by u of t. So now if we apply force from here, and it will start moving, and you know that when we apply force in this direction, so it will move due to this tires, and this mass also moves. So we have to write the equation for this system. Okay. Now actually we didn't apply any force on it, so let's see how equation look like. So here there's no force mentioned, so how we write the equation? We know that the same formula, F is equal to ma, but there's no applied force, so 0. There are some opposing forces that due to spring and damper, but they are in between y and u. So due to that reason, that means that this is equal to minus b times y dot minus u dot. Okay, due to the spring, due to the damper. Similar, due to the spring is minus k times y minus u is equal to m. M is with y, so it is y double dot. Okay, so let me rewrite here. Dots are not written. One dot here, other dot here. So this is the equation. So if we rewrite the equation on next page, so it becomes m yt double dot is equal to minus b y dot minus u dot minus k y minus u. So this is the answer that you are getting. If we look at the free body diagram, so we have a mass here. We didn't say we assume the massless, so if we don't assume, then we have to make another mass here, okay? But there's only one mass, so we have to make the mass. So there's no applied force, but this mass is moving in this direction due to this condition, we know that. So this is moving in this direction, and we have some, if they are moving in this direction, we have some opposing forces that are in opposite, and that force is due to the damper, that is y dot minus u, because they are between y and u. Similarly, k y minus u. Okay, so when we write it, so this is free body diagram. So from here we can easily write the equations. Okay, so now let's look some other examples on mechanical system to just make a good understanding. Now if I go to next page, is better. So this is another example here. So here we have two mass. This is mass 1, this is mass 2. Okay, so mass 1 is connected with a spring. In between there's a damper in between, and there's a spring, and this is a rigid body, and these masses are movable. So we put tire underneath it, and we call it mass 1, mass 2, then we call it as K2, this one is K1, and the other thing, this dash line means that this is a rigid body. Okay, now there's something like that. There's another spring here, and we call it is K3. Now we have to look at the displacement. Now this is the force applying here. This force is represented by U, and this is moving with x1, and this is moving with x2. So this is the basic, this is B here. Okay, so this is the diagram, and we ask you to write equations for this system. Okay, now equation for this system, how we wrote it. So what we do here, we make a free body diagram so that we can understand what are the forces and how they work. Okay, so for example, here mass 1, here mass 2. Okay, now for this one, if we look at mass 1, so there's an applied force in this direction. So all forces must be in opposite direction. So what are the forces that are in opposite direction? So put here, there are two forces that are in opposite direction, because this is moving with x1. One is actually due to this, what you say, mass of the system, that is x1 double dot. What about the other two forces? One is due to this spring, damper, there's another spring. So there are three actually. Okay, so first one is with spring, that is K1 x1. If we look here, this part, now we move to this part. Now this spring is between x1 and x2. So what we can do here, we put K2 x1 minus x2. Okay, alright. So we know that this is between this, and this force actually becomes applied force for this mass. Similarly, if we write for B is x1 dot minus x2 dot, and this is also becomes applied force for second mass. Opposing force for mass becomes K3, that is due to spring x2 and due to its own inertia. So if we write down equations, we get the result here, and equation becomes m1 x1 double dot for this one is equal to u minus, because we have to write all forces on one side. If we want, you can write it here with plus sign, doesn't matter, but we can do this thing as well. Or you can, second one is m2 x2 double dot is equal to, is there any implied force for this system? No, there's no applied force, but these forces become applied. So what applied force? First one is x1 minus x2 plus second one is b times x1 dot minus x2 dot. So, and we have opposing force, that is k3 x2. So these are the equations that you can get for this system. Now this is one way of writing the equations, and from here you can write the mathematical formulations and solve the problems. Okay. So there's another way of writing equations, and we will look at where you can easily write the, using the inspection method, you can easily write the transfer function. Now let's look at those examples, and for that we say that for inspection method, so it is something like this. You have to make a bracket here and wrote here sum of impedance connected to the motion of x1. Okay, sum of impedances connected to the motion at x1, and put here x1 of s, then put minus sign and wrote sum of impedances. Impedances mean that you have a damper and spring, okay, between x1 and x2, and put here x2 of s, then is equal to sum of applied forces at x1. Similarly, you can, when you start writing for x2, in that case it becomes sum of, same thing, impedance is x1 of s, then this becomes positive x2 of s, and this becomes sum of applied forces at x2. So this is the way you can write the equation. Now let's see the same example that we do in previous. Now look here, if we look at x1, for x1 there's applied force u, and there's no other applied forces, but the movement that with respect to x1 is k, and between x2 is this number. Okay. Now what we have to do here, we have to put here the values. So the movement with respect to x1, if you look here, so this is due to k1, k2 and damper. So if I say k1 plus k2 plus, for damper we have to put s, because this is not with the x only, this is with the velocity. So then we put minus, and we look what is with the x2. Look here, between x1 and x2 is this thing, and this is k2. Look here, k2 and b is with x2, so just plug in there and write k2 plus bs and put x2 of s, and equal to what is the applied force for this mass that is with respect to x1. So applied force is u. Now this is equal to sum of forces, that is u. But one thing you have to miss here, because the impedance is also involved the mass, because we are looking mass as well, so I have to rub this one, okay, and to put mass as well, that is ms square. I forget that. Okay, so this is my equation 1. Similarly for equation 2, I have to look at the second mass. So it is moving with x, and is there any applied force? No, of course not. So there's only one impedance, that is with kx2, and this is also mass. So what we do here, we put this thing and put x1 of s with a minus sign, with plus sign. First we try to write the x2. x2 becomes ms square plus k3 x2 of s. These two, but these are also between them, so we have to write this as well. So let me complete it. So we have to put plus k2 plus bs. Okay, this becomes x2 of s. There is no applied force, so it is 0 here. What about x1? So what is in between these two? That is k2 and b. So just plug here bs plus k2. So this is the equation number 2. So this is the way you can write equations directly if you want to find the transfer function for what you say mechanical system. But you can write from here to the equations as well, differential equations. How you can do it? So you know that this is second derivatives. Just put m x double dot plus kx1 plus k2 x1 plus b x1 dot minus k2 x2 minus b x2 dot is equal to u of t. Similarly, second one, if you compare this and the previous result, you get the same result for both equations. Now this is one way of doing it. Let's okay, now we will move to next thing, and we look at the rotational system, so that we complete this thing. Now for rotation, assume that something like this is a damper, and there is a rotating inertia. Then there is a spring, then there is a damper. So if I say this is J2, this is J1, so that be consistent with the variable, and there is another damper. Okay, so this is our system, and damper here is D2, here is D1, and they use D, it doesn't matter. So torque is applying here, T, and which has a movement theta 1, and D2 spring is connected, so there's another theta 2 is the movement, and so we have to solve this equation. Okay, now we will do similarly as we did in previous case. Now we have to look at this free body diagram. Now if we look at this damper, this inertia rotating one and this one, J2. So okay, so torque is applying here, so we do have some opposing, and theta is with this direction. We do have some opposing here, and opposing is with the damper, then D1 theta dot of D, and also with the spring, and spring is K theta 1 minus theta 2. So this becomes the applied force here, this direction. So that theta is applying in this, because this is opposing and this is in other direction. So here it becomes K times theta 1 minus theta 2, and we do have another opposing here, that is due to the inertia, and also due to the, I forget to write the inertia one, that is this one, and also inertia is G theta 2 dot, also with the damper, that is D2 theta dot. So this is the way you can solve just write the equation. The equation was sum of torques is equal to j theta. So applied torque is, and we have j1 theta 1 dot plus the opposing, that is d1 theta 1 dot plus k times theta 1 minus theta 2. Similarly, in this equation, there is applied torque, that is k theta 1 minus theta 2 is equal to j2 theta 2 double dot and plus d2 theta 2 dot. So this is the equation of this system. So we can write directly as we using the inspection method, and for first inertia we can say that sum of impedances that work on theta 1 of s, then put minus, then theta 2 of s equal to applied torque. So applied torque is T of s for first one. Now if we look at with theta 1, we have j1 s square plus we have d1s plus we have k s. Okay. So similarly, if we with between we have only one, that is k. Okay. Now for second equation, because there's only one and we say k of theta 1 of s, and with minus sign for plus sign, what we have j2 s square plus what we have, then we have d2s plus is there anything else? Yes, we have k. Similarly, is equal to, is there any applied torque? No, 0. So this is the way we can solve these equations using inspection method or by applying the Newton's law. Now one thing which we need to discuss before is known as gear ratio. Okay, so this is gear ratio. So what happened actually if we have a gears assembly that has some teeth, okay, and it is connected with another gear assembly that also do have some teeth, okay. So normally we use these to transfer. It is with radius 1, this is with the radius 2, okay. So we say that number of teeth here is n2, teeth here is n1. It is moving in theta 1 of t when torque 1 is applied, okay. So it will move in opposite direction with theta 2 of t, okay, with the torque 2 of t. Alright, so this is the radius. So now this is also known as input gear, and this is known as output gear. Now we have to transfer from input to output, because normally whenever we look at the transfer function, we need some phenomena that we can go from input to output. So for that case, we have this relation, and that relation says that when torque 2 divided by torque 1 is equal to theta 1 divided by theta 2, that is equal to n2 divided by n1, and which is equal to R2 divided by R1. So this is the relation that we can use to solve all these problems that are related with these relations. Okay, now let's do a very quick example so that we can understand. Now assume that there's a so something like this. This is connected with the inertia J, and a damper and a spring connected with a ridge body. So we say that damper is D, spring is K, and number of teeth here is N2, number of teeth here is N1, applied torque is T1, and with the angle is theta 1 of T. The other one is moving in this direction with theta 2 of T. Now this is what we get here. Now if we want to write the equations, so we can do that because there's only torque that is applying here. If we convert that torque and convert here, so we can use this. We know that theta 2 divided by theta, torque 1 is equal to theta 1 divided by theta 2. Or in other words, we can say that that is equal to N2 divided by N1. So we can use these relations and we can convert it. That we can convert theta 1 into directly here because the output is lying in this with load. So we just want to do it. So how we do it? From here we know that here is the also a torque that is T2. So we need relation between T1 and T2. From here we know that T2 is equal to N2 divided by N1 times T1. So T2 is equal to N2 divided by N1 times T1. So this is the relation. So second relation that we need is for theta, and we know that we can calculate this in terms of theta, or we can look at theta 2 and solve for theta 2 as well. Doesn't matter. Now we reduce this equation and further reduce to this one, that we have here we have a damper, here we have a spring, here we have a rotating inertial mass J, and they are actually applying torque, that is not T2, it becomes N2 divided by N1 T1, and with angle theta 2, and try to solve this equation. This make things quite easier. And for theta 2 we have to convert this. How we do that? We do same thing here. We know that theta 2 is equal to N1 divided by N2 times theta 1. So if we plug in here, we can replace this theta. Okay, so we have what you say, D here, spring here. So now if I go to next, to make things further easier, so we have a damper rotating inertia here, and we have applied torque, that is T1 times N2 divided by N1, and we have a angle applying, that is, we assume this is the theta 1, so we can convert theta 2 into theta 1 as theta 1 times N1 divided by N2. Okay, so if I check my yes, same relation. Now same thing we can do. We have a damper here and we have a spring here. Okay, so these damper and spring is with theta 1 actually. Now it will change with theta 2, and that becomes N1. Okay, leave it for a second just. Okay, because these are with theta 2, and we just have to write it. When we do write it, so we can say that okay, we have applied torque, assume that is theta 1, then this is equal to this must be if I let me write it full equation, then I simplify it. So T1 times N2 divided by N1 is equal to, we have opposing due to inertia, that is J time, actually theta 2. Theta 2 is equal to this one, theta 1 divided by N. So right here theta 1 dot times N1 divided by N2. Similarly plus We have a damper, and damper is also with theta 2. Just put theta 1 double dot and times n1 divided by n2, plus we have spring, sorry, we have a spring, and that is the torsional spring k times theta 1 times n1 divided by n2. Now if I calculate T1, so it becomes J theta 1 double dot times n1 divided by n2 square, plus similarly d theta 1 double dot n1 divided by n2 square, plus k theta 1 n1 divided by n2 square. So this is the way you can write relations for rotational system. So this is about mechanical system. So hopefully you understand it. I will stop here. Thank you.